So in last video we looked at the support vector machines and corresponding prediction model for predicting binary outcomes. So we compute something like table SVN. This is a tabular representation of the predicted outcomes versus the original outcomes. Essentially, to what extent the predicted outcomes agree or disagree with the original intended outcomes. So we kind of need to find out whether if the original value tends to be 0, does my predicted outcome also tends to be 0? And similarly, if my original outcome tends to be 1, does my predicted outcome also tend to be 1? Right? So that's where we measure the agreement. And a simple way to do that is to estimate kappa statistic. So kappa statistic essentially we can compute using a combination of proportional analysis and marginal analysis. They are built-in methods. You can do this by hand as well. So when I compute the expected, so what I do is I compute the expected behavior, I compute the observed behavior, and when I look at expected behavior, I need to understand what are the current prevalent patterns of zeros and ones, and what is the predisposition of me finding any given inclination by sheer chance. And to know that, I first need to compute what is my expected behavior, and that is computed here. And then similarly, we also compute the observed behavior, which is essentially what proportion of outcomes with their zeros or ones occur together. That's 0 occurs with 0, 1 occurs with 1. And I do that by computing the observed statistic or measure. And so these are my initial ratios. And then I would take a further ratio analysis where I compute the difference between my observed and expected behavior, and then I take that in relative to what is called as 1 minus expected, which is essentially the previous expected computation subtracted from unity. And this gives me the kappa value. This ranges between 0 and 1. So the value that we computed here is about 0.29. And there is a scale which typically, so I think just a correction from the previous sentence, the kappa value ranges between -1 and 1, not 0 and 1. So in this case, considering that it is 0.29, there is a moderate or weak form of agreement. So we are not sure as to whether the predicted model really agrees with the findings of or the expectations from the original behavior that is recorded. Now, another way which we did last time, this is a ready-made method. It's called class agreement. So I'll just pass on the table of computation for my current model, which is SVM, and then I would get the same computed value in terms of kappa statistic, which is 0.29. And I can do that also using the confusion matrix, which also does a range of other metric computation. We looked at accuracy, sensitivity, and specificity, and so on. We are currently interested only in the kappa value, which is again 0.2982. So that's a quick way to understand what kappa statistic is. Essentially, it tries to compute. It is a quantitative measure of whether we can conclude as to whether two different ratings or two different models agree with each other or not. And there are a few other functions. When we look at the outcomes, when we compare the outcomes with the original values, we would also like to explore whether we can penalize the difference or the dissimilarity. And that is computed through a variation of kappa statistics, which is weighted kappa. And here, what we are doing is just the way we compute a sum squared error. We are penalizing the error. Similarly, here we are penalizing the dissimilarity. So the more opinions or ratings disagree with each other, they would be penalized from